use symmetry to evaluate the integral from -2 to 2 of x to the fourth plus 2x squared dx. Now, in this situation, you might notice that both of these are even powers of x. So this is probably an even function. But if we're not sure, the way to test that out is if f of the opposite of x is equal to f of x, we know it's going to be even. So let's try that. In this case, f of the opposite of x is going to be the opposite of x to the fourth plus 2 times the opposite of x squared. And we know that when we raise a negative to the fourth power, that becomes positive. So that's going to be x to the fourth, and then plus. Also, the next term is going to be positive, right? The negatives cancel there. And this is equal to our original function. So because f of negative x is the same as f of x, we know that it's even. And so we can't say that the integral is equal to 0, but we can rewrite this integral as 2 times the integral from 0 to 2 of that same integrand. And at the very least, it saves us from having to plug in -2 when we can plug in 0 instead. So let's find the antiderivative. X to the fourth gives us x to the fifth over 5 plus 2x cubed over 3, evaluated at 0 and 2. When we evaluate that at 2, that's 2 to the fifth over 5 plus 2 times 2 cubed over 3. And we know that this is going to be 0 when we plug in 0 for x. So we're good to go there. Now let's see. 2 to the fifth, 2, 4, 8, 16, 32. So that's 32 fifths plus, what is that, 16 thirds. We're going to need a common denominator. That's going to be 15. This first one becomes 96 fifteenths, and the second one becomes 80 fifteenths. And then when we add those together, what do we get? 176 fifteenths. And I don't think that simplifies, but we can multiply that by 2. So that's going to give us, what, 352 fifteenths? And that is our answer. Not the nicest fraction in the world, but we can manage.